All right, let's go ahead and get started here. 626 or 620, and we're doing some Calc 2, and we're going to be looking at volumes. So this is kind of going off of finding area between curves and then bringing it to this new level of rotating these areas around certain axes. So let me just kind of put this down, and then we're gonna talk about it. I'm gonna have this volume, and I'm gonna set it equal to this integral from a to b of a of x dx. And what this a of x is an area function. So depending on what kind of functions we're looking at and which approach we kind of want to use, either from the y direction or the x direction, we can use general shapes that we know the area of, like a circle, or later on we're going to talk about cylinders. And we can use these to calculate volumes. So I guess the first way, or the best way to do this, is just kind of like jump right in, and then I'll kind of talk about it. So right now we're gonna start with problem 1 here, and we have y equals x squared minus 4x plus 5. Okay, and this is our first curve, or for this example, we're going to have this one curve, and I guess these are curves, huh? X equals 1 and x equals 4. And we're going to rotate it. So I'm just going to have this little rotating symbol here around the y-axis. So the graph, let me kind of do a little doodle here. Okay. Our graph here is going to look something like, so if we got x equals 1, and then it goes to x equals 4, something like this, and our curve kind of does that. And what we want to do is go ahead and find this shape rotated around the x-axis. I'm sorry. So up here I wrote the y-axis, but it's actually going to be the x-axis. So that means that the shape is being rotated around this axis. So it looks like kind of like a vase sideways, right? So now we've got this highlighted region here, and we know how to find the area of that thing using integrals. If we've got this y of x, this y of x and our bounds here. Now, what the trick is, if we're rotating around, how do we really calculate the volume of this thing? So because it's symmetric, we can take advantage of that. And in this case, we're going to use circles. So what do I mean by that? So if I've got this height of my function here, I know what that is. That's given to me by this function here, right? So any place up to there is given by that function, right? So how do we utilize that? Well, I've got a circle. Let's go ahead and see if I can get a good circle going here. Nice. Let's make it a little bit bigger, right? And I'm given a radius here. I can find out what the area of this circle is, right? The area of this circle is pi r squared, right? Well, if I put this circle kind of on this other graph here in terms of the height of the function, being my radius, so that one of those green lines here is my circle radius, and I kind of draw a circle here, and it rotates around, right? So something like that, right? We can calculate what the area of that individual really thin circle is, right? So this circle is really flat because we're only looking at this one point. Now, if we do that for every slice of this phase, we can come up with the whole volume. So that's what I mean by this A of x. So what we're going to do is use a circle and plug that into our original expression for volume. So this guy right here. So what I'm going to do now is write out what my area function is. So my A of x for this particular problem is going to be my first, of course, pi, and my radius squared. Now, my radius was given by y, right? So it's this x squared minus 4x plus 5 squared. I can plug that in, right? So my volume is, now because we're looking at y, or x equals 1 and x equals 4 as our bounds, of course, those are the bounds on our integral, right? Because we're going in the x direction. So I've got this pi here. And now I'm going to go ahead and just FOIL this guy out. This is x to the 4th minus 8 x to the 3rd plus 26 x squared minus 40 x plus 25 all dx, right? Now this is a pretty simple integral. Right, so now I've got this pi out in front, and now because I just have polynomial terms, I have a 1/5 x to the 5th minus 2x to the 4th plus 26 thirds x to the 3rd minus 20 x squared plus 25x. My bounds are 1, 4. You plug those guys in, we're going to get a 78 pi over 5. And that's going to be our area of the shape up here, rotated around the x-axis, right? So we're able to use circles to really define what our volume was going to be. And all we did really was find out what that area function is and then plug it into what our volume is, right? Because it's this area rotated around, and that gives us this volume, right? Because we have a two-dimensional thing. To get to that 3D, we're going to have to rotate it, right? So the first thing you should be able to do is look at the problem, kind of maybe get a rough sketch in your mind of what you're looking at, and then decide which direction, X or Y, is more appropriate, and then what kind of shape you should take. So the first few examples, we're just going to be using circles, but later on, we're going to be looking at cylinders. So that should probably give it away what first few steps for the next problem and the one after that. So what we're going to do now is jump right into number 2. So number 2 here is, so I'm going to list two functions now. Y is equal to the cube root of x, and y is equal to x over 4. Ooh, let's get a better 4. There we go. Right? And we're going to be only looking at the first quadrant. and we're going to be rotating around the y-axis. Okay. If you remember, the first quadrant means, let me do a little chart here, is 1, 2, 3, 4, right? So we're only looking at this guy up here. Right, and what this kind of looks like is, show my graphs here, and then we've got our, let's make it a straight line here, right? And then we've got this other function, this cube root, which is actually going to be like on top of it. Oops, sorry, got my my line thing still on. All right, so here we go, and this is what we've got in between here. And so the next step is to define what our area function is going to be, and then we got to find what our bounds on our interval. It's not as well defined here. Let me go ahead and put my rotating symbol in here. There we go. So we're rotating around the y-axis, so vertically. So we kind of got this, I don't want to say vase again, but maybe like a top that has the top of it cut out a little bit. So what's going to happen here is we're going to talk about our area function again. And of course, this is going to be equal to pi r squared because it's the best. Here's a circle. Now, it might not be the best to do it in the x direction, right? If we're doing this in the x direction, we're rotating around the y direction, we can't really get a radius, right? So the best thing to do is to start looking at y. So what we're going to do is convert what we have. So we've got this y equals the cube root of x. What that means is that x equals y cubed. And then our other one is 4y equals x. So now we've got these other functions that we've gotten from functions of the problem, and we can find our radius through that, right? So what I'm going to do is actually get rid of this x in here, right? And I'm going to put a y. Right? And now the radius of my circle is, so let's look at which one's going to be the larger circle first off, because we have to remember what we learned back in the area between curves, right? So if we've got these two curves and we're doing this method, we'll ultimately be finding this cone-like shape from the linear expression when it's rotated around. And then the top one will get this other this shape going. And when we subtract the total volume of the cone from the one that we found in the inside, then we'll get our final volume. So let me kind of highlight that. So the volume rotated around of that upper guy, we'll find that yellow part, right? And the whole thing that we're finding by the linear term is what we have in pink here, right? Now it's a little bit hard to see, so I'll get rid of the pink, but you get the idea. So what I'm going to do is have two circles, and so the larger one is actually going to be that linear one, it's that 4y, right? Square that radius, and that gives me the total volume, but I need to subtract that inner guy, right? So I'm going to subtract the y cubed term. So that gives me these two circles, and that gives me in total my area function. And what I can do from there is start writing my volume. But the first thing I have to do is also look at my bounds, right? Because I can integrate, but I have no idea what my bounds are going to be. So if we look at our functions, and set them equal to one another. So we've got this y cubed equals 4y. Right off the bat, you can kind of see that 0 is a solution here, right? And if I do that, so my y equals 0, right? Then I can divide both sides by y, right? So I've got this y squared equals 4, right? And then that's going to give me y is plus or minus 2. But remember that I'm only looking in the first quadrant. So I should only be really looking at positive 2, right? So we're going to be going from 0 to 2. So I'm going to set up my integral. My volume is equal to the integral from 0 to 2. And then my area function, this pi. And then what I'm going to do now is just go ahead and simplify this a little bit or FOIL it out. So we got 16y squared minus y to the 6th dy, and that's a pretty easy integral, right? We've got pi 16 thirds y cubed minus 1/7 y to the 7th from 0 to 2. Plug those guys in, and you will get 512 over 21 pi. Okay. So what we've kind of learned from this is that we can bring in the methods that we learned for finding area between curves and kind of put that methodology for volumes as well. So we were able to use a circle in the y direction and have these two curves instead of just one. So again, ultimately what we've done is we found the total volume rotated around for the linear, which makes this cone-like shape, kind of like this, right? And then we found this other guy that's like this sliver part, and we found the area inside there as well. And then we were able to have this total area and then subtract and then get just what we have for the yellow. So what we're going to do now is look at another example, circle, and then we can move on to something a little bit more interesting, the cylinders. So we've got number 3 here. And write out what we've got. We have y is equal to x squared minus 2x. And then our other function here is y equals x. And then what we're going to do is rotate around y equals 4. So we're no longer rotating around one of the axes, y or x, but what we're doing is rotating around another line. Right? In this case, it's y equals 4. So what this kind of looks like is, I'll draw my graphs here. And actually, we're going to dip below a little bit. So we've got our y equals x line. And then this other guy comes does this. Right? So now we've got this area here. Now we've got this y equals 4. So it's this line up here, and we're going to be rotating that around. Okay? So in fact, these shapes don't even, this region here, this pink region, doesn't even touch the line that we're rotating around. So it's a little bit harder to think about. So the first thing we should do is, since we're considering circles, and since we're rotating around this horizontal line, you can imagine that we're going to go in the x direction, so that our y values are the radius, right? So we're going to have to talk about this this inner radius and outer radius of this shape that we need. So let's go ahead and look at our inner radius first. Inner radius. Okay. And what this really is this region here from this line down to this shape, right? So since we have y equals 4 and we're going down to this top line here, which is actually y equals x, that radius for that circle is going to be 4 minus x, right? Because, so if we've got this region 4 here, and we subtract this y equals x, this x component, then we get the distance between those two, right? Which is this 4 minus x, and that's going to be your inner radius. Now, our outer radius is going to be from that line all the way to the bottom curve, right? So that guy is going to be 4 minus, and then we have our function there as x squared minus 2x, right? We can simplify that guy a little bit, and we have minus x squared plus 2x plus 4, right? So now that we have our inner and outer radius, we can actually define what our area function is. Okay. So we've got our pi, and now we're going to do two circles just like we did for number 2 with the larger circle, and then subtract the smaller circle. So the larger one is actually going to be the lower line, right? So we're going to have this negative x squared plus 2x plus 4 squared, and then subtract the smaller circle, which in this case is the 4 minus x squared. Okay. So now finding the bounds on these guys, we can set them equal. We've got x squared minus 2x equals x. Again, you can kind of right away see that 0 is a solution, right? Then we've got this equation if you divide through by x, right? And then that means that we've got 3, right? So now we can set up our integral. Let's go ahead and volume 0 to 3 pi. And then let me go ahead and FOIL this guy out. X to the 4th minus x 4x cubed minus 5x squared plus 24x dx. Right? And we go ahead, do this integral. We're going to go ahead, because it's an easy polynomial, we have our 1/5 x to the 5th x to the 4th minus 5/3 x cubed plus 12x squared from 0 to 3. And this leaves us, put those guys in, 153 over 5 pi. Right. So again, the first step you should be taking is decide what kind of shape you want to use, and going ahead and finding this a of x or a of y functions, your area function, and then just plug it on in into the volume integral, right? Make sure you've got your bounds. So the difference between this problem and the other problems was that we were rotating now around this line that wasn't just the y-axis or the x-axis. So we had to kind of redefine what our radiuses of this circle were going to be. Okay. So what we're going to do next is look at cylindrical shells. Let me go ahead and start. We got cylindrical shells. So the volume of a cylinder here is, all right, so we've got our volume term here. And we're going to just go ahead and add up all those cylinders. Okay, so for number 4, we're going to be looking at y equals x minus 1, x minus 3 squared. And then we're going to rotate this guy around the y-axis. Okay. What that kind of looks like. Is we've got this little tick marks right here, and then our function kind of looks like this. And we're going to be rotating it around the y-axis, so we're going to go around this guy. You could use circles with this. It's a little bit harder because this one function defines both of your radiuses, right? Because if you're going to use a circle, you're going to have to take the radius of that and then take the radius of that. So it doesn't really pass the line test in the y direction. So it's kind of hard to use circles. So we're going to be using cylinders instead. So what we're going to be doing is taking cylinders in this direction and then rotating them around. Right? So first, let's go ahead and find out exactly what the area function is going to be looking like. So if we subtract 2 of these volumes, and the book does a really good job in the first section of 7.3 of describing that. So if you want to take a look at that, go ahead. It's only just a few lines, but we've got this as our volume. Okay? So 2 pi r h, and then delta r, which is the change in the radius from one shape to another shape. Luckily, we only have this one shape to be worrying about. So let's go ahead and find what our area function is going to be. So we're going to set this equal to 2 pi r h, right? And in the case of this problem, our radius for our cylinder is just simply going to be, I have an x there. The radius of our cylinder is just simply going to be x here, right? Because as we go further and further down the line here, we're going to have a different value of x, right? And that's going to be the radius of our cylinder that we're rotating around. Now the height is given by the function, right? Our y. So in terms of x, we've got x minus 1, x minus 3 squared. Luckily, we don't have to square the y term like we had to do in the circle case, because that can get kind of messy. So now that we've got our area term, we can go ahead and find what our volume is. And by just kind of looking at the y function, you can see that x equals 1 and x equals 3 are the zeros for that function. So those are going to be our bounds, right? And then we've got our 2 pi, and then our x. And then, so what I'm going to do is actually multiply that x into the other parentheses so that we've got just a polynomial. And that leaves us, once we FOIL it out, is this x to the 4th minus 7x to the 3rd plus 15x squared minus 9x dx. Again, this is a pretty easy polynomial. And we've got 2 pi 1/5 x to the 5th minus 7/4 x to the 4th plus 5 x to the 3rd minus 9 halves x squared from 1 to 3. And plug these guys in, we're going to get 24 over 5 pi. Right? So we were able to use cylinders in this case instead of circles. So generally, I think circles are pretty straightforward to use. It's all what you kind of feel more comfortable with, but sometimes one's better than the other. In this case, we explained why a cylinder is better because the function itself is defining the 2 radiuses that you would use for a circle, which is problematic. So we went ahead and used cylinders instead, so we could use the y values rather than the other direction. Right? So let's go ahead and look at our final example here. So number 5. And we've got y is equal to 2 radical x minus 1. And our y equals x minus 1. And we're going to be rotating around x equals 6. So we're going to be rotating around another line other than the y or the x-axis, just like we did in number 3. Now we're going to be using cylinders. So the shape kind of looks like, well, first we got this line here, and then there's a curve. And then we're going to be rotating around some vertical line over this way. We've got our area inside here, and then rotate it around. So we're going to use cylinders for this guy. And so let's go ahead and start writing out what our area function is going to be. So we've got this a of x, and this is going to be equal to our 2 pi. And now let's talk about what our radius is here. So our radius is going to be the distance from this line over to whatever we're looking at. So so let's say we've got a cylinder right in here, right? And this is what we're rotating around. We've got this cylinder right in here. The radius, oh, well, I should really be rotating around this whole thing, right? So our radius here is going to be this segment here, which is at some x. And then we've got our line here, which is at x equals 6. So the distance between those two is 6 minus x. That's our radius. Whereas our height is going to be the difference of these two functions. So we've got 2 square root of x minus 1. And then our linear term, right, because we're subtracting it, that's why the sign switched. And then we can go ahead and start trying to find this volume. So before I do that, let me just kind of simplify this. So we got 2 pi. For this guy out, we have x squared minus 7x plus 6 plus 12 radical x minus 1, and then minus 2x radical x minus 1. Right. And now we have to go ahead and find these bounds. So I'm going to do all this to the side right under the graph. Set these guys equal. We have 2 radical x minus 1 is equal to x minus 1. And so if x is 1, both of the sides are 0, right? So that's our first guess, right? And then we got x equals 1 here. So the other one is actually x equals 5, and how we can get that other than just kind of seeing that we plug in x equals 5, we get the answer here, is that if we divide over the 2 and then square both sides, we can get the answer that way. So we have x minus 1. And then, so what I've done here is squared both sides after dividing off the 2. Right? And then this will lead you to x equals 5. Right? Because once you FOIL that out, you can get a polynomial, or you can divide both sides by this x minus 1 term. Right? And that will just give you 1 equals x minus 1 over 4. So then we have 4 equals x minus 1. And then we can get our x equals 5. So now we've got our final integral here from 1 to 5 of what our area term was. So our x squared minus 7x plus 6 plus 12 radical x minus 1 minus this 2x radical x minus 1 dx. So the first few terms are polynomials. So those are pretty easy, right? So looking specifically at this term here and this term here, those are going to be a little bit trickier. The first one is pretty easy in the sense that it's just a u substitution, right? X minus 1 is your u, and then it just kind of follows from just a normal polynomial. The second guy, however, is also another u substitution with x minus 1, but once you do that, you have to sub out that x that's out in front in terms of u, and then it kind of splits up into 2 polynomials. So in the end, they're still pretty basic integrals. Try it for yourself. And I'll give you guys the next line here. We have 2 pi. So this is pretty lengthy, so we'll probably have to use those 2 lines here. X to the third minus 7 over 2 x squared plus 6x plus 8 x minus 1 to 3/2. And then we're going to have to subtract 4/3 x minus 1 to 3/2. And then we've got 4/5 x minus 1 to 5/2, evaluated from 1 to 5. Plug those guys in. We're going to get 272 over 15 pi. All right, so we were able to use cylinders for this guy and rotate it around another arbitrary line here. So we've got this x equals 6 and rotating this shape around using cylinders. So the next section is about arc length, and for those of you that haven't started reading that section, or you have, I think the best way to kind of get into arc length is, and I know the book kind of goes over it, but a fun fact is back when I was taking Calc 2, my instructor asked us, how would you calculate this arc length? And gave us a hint, saying you got to use integrals, right? Integrals are adding up these really small segments of things. So how would you go ahead and calculate an arc length? So the length of this curve. And I'll kind of give you guys a hint, and I want you to think about this before we meet on Wednesday, is how to calculate this. And the distance between 2 points is something that you guys can learn, or I mean, you guys should know, right? And if you move those points really close together, you should get something in terms of what kind of notation we've been using in terms of like dx's and dy's, and then add up all these really small segments together, right? Because a closer approximation would have some kind of curve, right? We've got some kind of curve like this guy. Go ahead and draw something. And if I wanted to break up into one segment, it's a decent approximation. But if I did 2 segments, it's probably better. And if I did 3 segments, it gets even better. And if I keep doing that over and over and over, I get closer and closer to the actual arc length. So that's where the integral takes over, right? Because we're doing these really, really small segments. So go ahead and just think about that for a little bit. And then we'll talk about it on Wednesday. If you guys have any final questions for me, let me know. Again, I apologize for the little bit of delay of the recitation for today. I was actually hit by a car while I was on my bike, and the recitation kind of flew over my head. Still, I should have been here on time. Head was a little clouded, but I'm okay. I'm, for the most part, okay. A little bit of some wrist injury, but we'll recover. So now, the next time I will meet you guys is on Wednesday, and we're going to going to go over some arc length, and the next section, I think, is we can start trying to go into area of the surface revolution, so 7.5. It takes the concepts that we've learned here today with volumes and rotating things around, and inserts the knowledge that you guys will learn with arc length into that, which is a pretty interesting topic. And then we're getting into the good stuff. We're going to be getting into a lot of applications for engineering pretty soon. So I'm going to end this recording since you guys don't have any questions. And then, yeah, just shoot me an email if you have any problems or any questions. A few of you are doing that now, and I really appreciate it. And I hope I'm giving good feedback. So keep up the good work, and I will see you guys on Wednesday.